Hi, welcome to Chem 6161 stereoselective reactions. This is a chalk and talk of the allylic strain lecture. First, we will define what is allylic strain, or what I want to obtain talking about allylic strain. Allylic strain is when we have a double bond and I have a chiral center in the allylic position. For example, this compound. Okay, here is the double bond, and here I have the chiral center. One carbon away, allylic position of the double bond. Okay, if I want to do a reaction over the double bond, whatever it is, I can do epoxidation, I can do a cyclopropanation, I can do a hydroboration. Okay, remember that a double bond is a very versatile functional group. Okay, because this position is chiral, this position will determine which will be the major diastereomer of the final compound. For example, I will put an easy example. If I do epoxidation with MCPBA, metachloropyrbenzoic acid, I can get two different products. The first one will be the epoxidation that took place from the face of the double bond that is in front of the slide. I get this epoxide, or I can get just the opposite. That the epoxidation takes place from behind the slide, and I get this final product. Taking account that these two products, because this chiral center remains the same, because I didn't touch it, I didn't do anything with this chiral center, these two products are diastereomers. In the lecture of today, what we will do is to know how to predict which will be the major diastereomer when we have a chiral center here. Okay? Good. The first thing that we need to do in order to determine how this chiral center will affect the double bond is to draw the lower conformation of this compound. Okay? The lower conformation in this type of compounds always is putting one substituent in the same plane that the double bond and facing down like the double bond. Okay? Then we have to consider which is the most important interaction. Here, the most important interaction will be the clash, the steric clash between this substituent of the double bond, in this case a hydrogen, and this substituent that I put here. Okay? Because these are in a syn-pentane interaction. If I put something big here, will clash with the hydrogen and will destabilize the structure. What I want to do is to put the smaller substituent in this position. The smaller substituent of this chiral center is obviously the hydrogen. This is the smaller one. That means that I will put the hydrogen here. Okay? If I put the hydrogen here, okay, if I move the compound, means that the phenyl is in this position and the methyl is in this position. Okay? I didn't do anything, I only rotate this stereocenter in order to put the hydrogen down, in order to minimize the syn-pentane interactions, and then, because I rotate, the phenyl is coming in front of the slide and the methyl is coming inside of the slide. If I do this, what is happening? Now the MCPBA okay, is attacking attacking the double bond. And the attack can take place from in front, that I will draw like this, okay, in front, or from behind. Okay, the approach of the peracid, in this case the metachloroperbenzoic acid, can be from in front of the slide or from behind of the slide. What happens if the attack is coming from in front? Well, if it's coming from in front, what is happening is that this perbenzoic acid is clashing with a phenyl ring. While if the attack is from behind, this peracid is clashing with the methyl. Which approach will be easier? Obviously, the easier approach will be the one that has less steric hindrance. In this case, the perbenzoic acid will attack from behind. That means that when I do this reaction, the major diastereomer, I don't say that it's impossible to get both diastereomers, I only say that the major diastereomer will be the attack from behind, and I will get this component. This will be the major diastereomer. Okay? And that's all. It's all what we need to know in order to predict the stereoselection in this type of reactions. I have a double bond with a chiral center in the allylic position. What I have to do is to put the smaller substituent in the same plane of the double bond, and then check which trajectory will be the less steric hindrance, will have the less steric hindrance. Okay? Some considerations. Well, it's very easy, but we can consider some other things, like for example, what is the difference if I am using a cis or a trans? Okay? What is the difference if I use this compound or this compound? How to predict which will be the major diastereomer is exactly the same way. I have to put the smaller substituent down. I will show you here. Okay. In both examples, in the cis and the trans, the approach of the perbenzoic acid will take place from behind the whiteboard, as I showed you before, because the approach will take place where they find the less steric hindrance. Obviously, a methyl is smaller than a phenyl. However, in this case, the stereoselectivity will be lower than in this case. That means if, for example, here we have 2 to 1 between the two possible diastereomers, here I will have, for example, 10 to 1. Why? Because in this case, as I have a substituent in this position, in the cis position, I am increasing the syn-pentane interaction. Okay? making that this conformer that has a lower energy will be by far less energetic than the next one. And I have a metal here, because I have a huge interaction between this R prime and the metal, makes that the energy of this other conformer be a lot higher. While here, if I have a hydrogen here and I put a metal here, obviously the energy will be higher than not to having a hydrogen, but the difference will not be so much. Okay? When I increase the steric hindrance in the cis position, more stereoselectivity I will have. Okay? Good. Then, now I am doing reactions that are based in steric hindrance. But what happens if, for example, I am doing a reaction with a reacting group? The most clear example is the Simmons-Smith cyclopropionation. Okay, the Simmons-Smith cyclopropionation basically is a cyclopropionation that takes place in a double bond that has an alcohol in the allylic position. Okay, normally the Simmons-Smith cyclopropionation is made with this compound, diuromethane, zinc, and copper. Okay, and what is happening is that the reaction takes place by the same phase where is the alcohol. Okay? In this case, okay, I already put the most stable conformer, okay, the smaller substituent in the same plane of the double bond facing down, and now the only difference than before, in the example before, is that I will not consider the steric hindrance. I know that the reaction will take place by the same phase where is the alcohol. Okay? That means, in this case, this will coordinate with the oxygen of the alcohol and will take place for the same phase. That means that I will have this compound where the cyclopropionation takes place by the same site, the same phase, where is the hydroxyl group. Okay, if I have another example, for example, I have this compound. Okay, I have this compound, I am doing exactly the same reaction, the cyclopropionation, the Simmons-Smith cyclopropionation. What I have to do? Okay, first I have to transform this with the lower conformation, with the lower energy conformation. How I do it? I put the smaller substituent down, in this case a hydrogen, and then, because the hydrogen is down, I rotate, and the lowest conformation is this. And now, because I know that it's a Simmons-Smith cyclopropionation, I know that it takes place by the same site of the alcohol, and this will lead to this compound, with the cyclopropionation taking place by the same phase where I have the alcohol. I don't care about which phase will be less hindered. The only important is where I have the alcohol. This is called when we have a directing group. That is the group that is directing the the attack of the region over the double bond. Okay? Maybe you are wondering how we know if it's a rejecting group or not. Well, basically, I will indicate in the exercise if we have a rejecting group or not. Okay? If we are working with a rejecting group or we are working only by steric hindrance. Okay? And that's all. This is the lesson. This is only how, it's an example of how to draw all the transition states and all the conformers. Okay? And remember that this is a summary. You have to read the lecture, you have to attend to the lecture, and you will see that it's complementary. In the lecture we will put some more examples of rejecting groups, and we will explain a little bit in more detail the difference of energy between the different conformations. But basically here what I want to show you is how to draw the transition states, how to draw the most stable conformer, and I hope that you find this quite useful. Okay? Thank you very much for your attention, and see you in the next lecture.